In this lecture, we're going to start looking at a new reaction called the E2 reaction. So the E2 reaction shares many similarities with the SN2 reaction, but hopefully the differences aren't too overwhelming. It does have a different mechanism, but it's just one of these things where the more of these kind of mechanisms we see, the more kind of combinations of curly arrows we use, the more comfortable we'll get with new chemical reactivity. And so the reaction is called the E2 reaction. Goodness, sorry, highlighters on. It's the E2 reaction. So the E2 reaction, what you want to focus on is the E and the 2. This is short for bimolecular elimination. So we saw the 2 for bimolecular in the case of the SN2 reaction. So this is very similar. There are two concentrations in the rate law for the rate determining, or in the rate law for the reaction. And alternatively, you could say there are two, I'll kind of go back here, two reactants in the rate determining step. Okay, so these all sort of mean the same thing. Now, for us to understand what this process is, we have to break down the other word, which is elimination. So elimination reactions generate alkene products. So alkenes are molecules with one or more CC double bonds. And so what we're talking about here would be something like this, something like this, something like this as examples. Okay, so we have the bimolecular elimination reaction. Now, the general reaction is as follows. The general reaction is we take a haloalkane and we add this to a base to generate an alkene plus H base. Now, what I usually do is put a negative on the base. Okay, so this is the general reaction. Now, what I hope that you see is that this looks a lot like the SN2 reaction. So recall, so this is the general reaction for the E2 reaction. So we could recall for a second the SN2 reaction, which was haloalkane plus nuke minus gives rise to substitution product plus a salt. So in a lot of ways, the E2 reaction sort of looks like the SN2 reaction, and it has a lot of similarities that are useful to kind of consider when you're learning about the E2 reaction for the first time. Now, what I want to do is go right into the rate law for the E2 reaction. So the rate law for the E2 reaction, if you remember what a rate law is, that's just rate equals some rate constant times the concentration of, put a dot here for times, concentration, that's not how you spell concentration, excuse me, of reactants in the rate determining step. Now for the SN2 reaction, For the SN2 reaction, it was rate of the SN2 reaction is equal to some rate constant K times the haloalkane, which was our electrophile in this context, times the nucleophile. We put those haloalkane and nucleophile in brackets to indicate concentration. So the rate for the E2 reaction is very similar. It's equal to K times the haloalkane as a concentration times the base as a concentration. So it's the haloalkane times that negatively charged thing. And so this is the rate law. And I'm going to go ahead and write this again up here, which is equal to, I'm going to put haloalkane as Rx, some R group, oh gosh, rate constant. I better just redraw this. Rate constant K, it's a little k, times Rx times base minus as concentrations. Okay, just so we have it in both places as you're reviewing your notes. Okay, so this is our rate law, and what this sort of suggests is if we consider the reactants again, the reactants were just the haloalkane and the base, and then the products were this alkene, this elimination product, plus some H base is what I'm calling this and referring to this as. Now, what all that means, what I'm kind of getting at, and probably not being a good job, doing a good job of clarifying, is that if we know this is the rate law has everything that we put into the reaction probably doesn't have any intermediates, right? Because we put everything into the reaction. If it's all involved in the rate determining step, we don't need additional steps to consume additional aspects of the reaction. And so with that in mind, like the SN2 reaction, the E2 reaction is concerted. And has 0 intermediates. Okay, so the E2 reaction is concerted and has 0 intermediates. And what that means is we can consider the energy diagram. For the E2 reaction as being the following. Let's go ahead and add our coordinates. So we have reaction coordinate along the x-axis, and then we have free energy delta G along the y-axis. And what we're going to do is generally we start higher in energy and end lower in energy, but we first have to go over a hill and then down to a lower valley. So this left-hand ground state, or left-hand well or valley in our energy diagram, is the starting materials. The right-handed valley is our products. And then we have only one transition state. One transition state. Okay, so in this case, then the starting materials are the haloalkanes plus the base, which I'll draw as a negative, and then the products are, and one thing I keep sort of forgetting, and that's my bad, we have the alkene plus the H base, and you actually also have X minus, which is our halide. So that would be like Br minus or I minus or Cl minus. And I've forgotten that as I introduced the reaction. It's not a big deal. It's one of these byproducts that we just lose, but I should have been more consistent. That way you can see the charge balance, where if you have some base on the left side and I say that's negatively charged, we have to make up for that with something negatively charged on the right side of the chemical reaction equation. Okay, so here it is. Here's our reaction energy diagram for the E2 reaction. Now, what we haven't actually done yet is even a single E2 reaction. So let's go ahead and look at an example of this. Before I do, I want to introduce the players, or the typical candidates. And the ones we want to focus on are the E2 bases. So the E2 bases are are kind of things, molecules, I guess. And they're really salts, but molecules that promote E2 reactions instead of SN2 reactions. So what I'm getting at here is that in the SN2 reaction, we take something with a negative charge and we add it to our haloalkane to form a substitution product. I haven't been super clear yet, but what we're doing with the E2 reaction is we're doing that negatively charged thing is acting as a base instead of a nucleophile. Now, these are things with negative charges. So how do we make sure that our negative charge thing is acting truly like a base and not a nucleophile? Well, we use special versions of negatively charged things. So the E2 bases are, I like to pick one of these two molecules. And so what we have here is potassium, tert butoxide. And so you can kind of see the tert butyl group on this molecule. And then you can see the potassium and then the oxide. Better pick a different color. The oxide, that implies that we have an O with a -1. This is also drawn as KOT bu, where we have our O, our T bu for T butyl, and then our potassium. Okay. Now over here, we have the molecule LDA, which is lithium diisopropyl, and then I hate the last part of the name, but amide. So lithium we can do, and I should highlight well, no, I don't want to do that. Okay. The diisopropyl are kind of these two isopropyl units. And then the amide is just actually a horrible name. So amide is one of the most important functional groups in chemistry and biology. But in this case, amide is sort of old name. This is the old name for N-. Okay, so these are our E2 bases. Now, if you notice, I said the base had a negative charge, but neither one of these molecules actually has a negative charge. Rather, both bases dissociate to give the negative atom. That is to say, if I take either one of these molecules, potassium tert butoxide, which I'm drawing here, or lithium diisopropyl amide, LDA, which I'm drawing here, and we mix these with the appropriate solvent, we're going to see dissociation to form this molecule and this molecule. So we have our O- and our N-. Now, with these two formed, we have our basic atoms present. Now, basic atoms in this case means that these atoms desire to pick up an acidic hydrogen. So I've got here H+. H+ is kind of the go-to acidic hydrogen. We're not going to actually use H+ at all for these reactions, but I just wanted you to see that what we're going to do is let our E2 base dissociate to form the free anion. I guess I'm drawing this a little rotated. And then that free anion will find a hydrogen atom to combine with to give our H base. So these are the H bases that I referred to when I balanced the chemical reaction. We could even draw curly arrows. Negative is attracted to positive. Okay. So it's these two bases that we're going to be using to actually do our E2 reaction. There are a lot of bases out there that can do this, but it takes some work to kind of, I guess what I'm saying is it's important to be able to recognize the reactant and know whether you're going to do an SN2 reaction or an E2 reaction. We're going to practice that later on. Like if you see some set of reaction conditions for a haloalkane, how do you know if it's an SN2 reaction or an E2 reaction? Well, instead of having you, what I would prefer is for you to just know the very common E2 bases. These are two very common E2 bases. And if you see them, recognize that you're going to try to do an E2 reaction whenever possible. Okay, so let's actually do the reaction. So what I'm going to do is take this molecule and react it with this molecule, and I want to predict the products. So if you saw this reaction, the first thing I would want you to recognize is that, okay, well, wait, we have a potassium here. We can cross that out and replace it with a negative charge. And then all of a sudden, whoops, that's not what I wanted to do. Then all of the sudden, we want like an alarm to go off in our head to notice that this is an E2 base. And so we assume that there's some solvent over the reaction conditions. I don't know, DMF, sure, okay, whatever. So we have some solvent. But what we want to recognize from an E2 base being present is that we're actually going to do an E2 reaction. Now, after you get comfortable with the mechanism for this reaction, which I'm about to show you, you will be able to predict the products then. And so the products are this, and this is the important product that I want us to care about. The other things I'm about to draw are byproducts. And just like the SN2 reaction, we don't have to worry about those so much. So that's our product, plus we're going to have KBr, plus we're going to have this molecule. So this molecule is our H base, and I'm not too worried about this. And this molecule is our salt. This is where our leaving group, the bromine, is just being countered by the positively charged counterion that we use for the E2 base, which in this case was potassium. But it's the thing I've highlighted in yellow. That's our alkene product, a molecule with a carbon-carbon double bond. That is our alkene product, our elimination product that we want to be able to predict and that we want to care about. Okay, so what's happening here? How is this reaction working? So far, it probably doesn't make sense. And that's okay. It's not supposed to make total sense. You're not really supposed to be able to predict it that easily until you know the mechanism. So the mechanism is again concerted. That means everything's going to happen in one fell swoop without the involvement of any intermediates. So what I'm going to do is redraw the starting materials along with the E2 base, but I'm not going to draw the counterion. I'm just going to go right to a negative charge. Now, what happens in this reaction is if we start at the haloalkane carbon and we go to a carbon next door triangle, what I want you to notice is that there are 3 hydrogens at that next door or adjacent carbon. So triangle is the adjacent carbon with adjacent hydrogen atoms. Okay, so what happens here is the negative charge actually engages the hydrogen atom and attacks that hydrogen atom directly. Now, hydrogen can only hold 2 electrons in its octet. So if it feels the effect of two electrons from a lone pair attacking it, it's going to lose whatever it's bonded to. So in this case, the carbon-hydrogen bond is going to break, and that's going to push electrons over. Now what's going to happen is we're going to move those electrons to form a new bond, a new carbon-carbon double bond, instead of forming like something with a negative charge or a new lone pair of electrons. We're going to move the electrons from a bond to a bond. And when we do that, we get a carbon-carbon double bond between triangle and circle in this case. Now there's an issue. If you look at carbon circle, the carbon that's highlighted with that dot or whatever, it can only hold it can only have 4 bonds or 8 total electrons. And so as it's accepting a new bond that's the form of a carbon-carbon double bond, it has to lose something. Well, the easiest thing to lose is that thing that's been a leaving group the whole time in our SN2 reactions, and that's the bromine. So we're going to let the bromine just sort of fall off. So the E2 reaction has 3 arrows. One arrow is going to show the base grabbing a hydrogen atom adjacent to the carbon with the halogen atom. Then we're going to have a second arrow to show that the carbon-hydrogen electrons are actually going to be converted into carbon-carbon double bond electrons. We're going to form a second bond between the 2 carbon atoms, the carbon atom with the halogen atom leaving group, along with the carbon atom that had that adjacent hydrogen that was removed by our E2 base. Then the leaving group, the halogen atom, is going to do what it does best. It's going to leave. So always 3 arrows, grab the hydrogen, make the double bond, push off the halogen, and that will give rise to a new carbon-carbon double bonded system, along with our H base, which we don't need to worry about after we get the hang of this reaction, along with our leaving group, which in this case has left as a negative charge. We have an overall negative charge on the left side of our reaction mechanism and a negative charge overall on the right side of our reaction mechanism. So we've balanced charge, we've balanced atoms, and we've shown how this reaction works. So what's really nice about the reaction is once you get the hang of the mechanism, it's fairly easy to predict what the products are going to be. You look for the carbon atom with the halogen, and then you find the adjacent hydrogens. Now, I would be remiss if I didn't actually teach you a proper name for these things, and that is the word vicinal. So vicinal hydrogens are H atoms on a C atom adjacent to the C atom in question. Okay, that was awkward. That was awkward to write. Alternatively, or they are H atoms, 2 bonds. Let's see, no comma there. H atoms, 2 bonds away from the carbon, or 3 bonds from X, which is our chlorine, bromine, or iodine. Okay, let's write this down. It's a lot of words, and it's 2 possible explanations, and it may not make as much sense as the actual picture. And this is just one of those classic examples where pictures are worth thousands of words, right? Okay, so maybe it's just easier to say, okay, let's look at a picture of this. So I'm going to turn the page and just say the picture view of a vicinal hydrogen is, let's just also call these adjacent H atoms, are if we have our bromine, chlorine, and our iodine, the H atom that's on the carbon next door, or the carbon 1, 2, 3 bonds away, this is our vicinal H atom. Okay? So it's this little framework of a 3 bonded system where you've got your I call it my haloalkane carbon. Without this carbon, which is bonded to bromine, chlorine, or iodine, without that, I don't have a haloalkane, right? Because if I don't have that, I don't have my halogen, and I don't have my haloalkane then. Then triangle, this is my adjacent carbon, and my adjacent carbon has the vicinal hydrogen atom. Okay. So what we can do is just recognize then that the E2 base looks for and removes, the process of removing this is deprotonation. It's just the chemical reaction where a base removes an acidic hydrogen, deprotonation. You've removed a proton, which is just an H plus equivalent, right? We don't take the electrons, we just take the nucleus, which is just the proton, so it's deprotonation. So E2 base looks for and removes, by deprotonation, the vicinal hydrogen atoms. Okay. So let's take a little bit of time at the end of this movie to practice some E2 reactions. I think that would be like a really productive use of time. So let's look at a few examples here. So let's say we've got HI, HBr. We'll do one like chlorine example, but everybody loves Br for these. Okay, so let's go ahead and do this. Now, let's add some bases. Let's kind of mix it up. Let's throw LDA in there a few times. Then maybe I draw the structures. Okay. So in all of these cases, let's imagine that we have our E2 bases committed to memory. If we have our E2 bases, then we should recognize that we want to do an E2 reaction. Okay, so what we have to do in every case is find the vicinal hydrogens. And so what I'm going to do is for each of these examples, I'm going to go through and identify the vicinal hydrogen atoms. So what we did was we went from the dot to the carbon next door. And if you notice, in this first example, we've actually got 6 times vicinal H atoms, 3 on either side. And so what LDA could do is it could grab either one of them. So I'm going to draw one arrow to grab, in this case, we'll just grab the right one. A second arrow to move the carbon-hydrogen electrons over to make a carbon-carbon double bond, and then a third arrow to push off the leaving group. The electrons sort of jump on the iodine and the iodine floats away. The product of this is I'm going to redraw my carbon atoms. Here's my dotted carbon atom. Now what I'm going to do is replace instead of having an iodine, that bond is gone. And instead of having a hydrogen atom, that bond is gone. I'm going to replace those missing bonds on the dotted or the labeled carbon along with the adjacent carbon with a carbon-carbon double bond. So the product of the first E2 reaction is shown here. We've lost the halogen and replaced it with a carbon-carbon double bond between the carbon that had the bromine, or excuse me, the iodine, between the carbon that had the iodine and the carbon that had the vicinal hydrogen that we removed. Now we could have picked one off the left side. The arrow would just have to be drawn a little bit further, but that would have actually given rise to the same product. In the next lecture, we'll look at what happens if we can form multiple products. But for now, let's just stick to one example. So similarly, I've got my haloalkane carbon highlighted with this dot, and then I'm going to consider a vicinal hydrogen, and there's actually 4 vicinal hydrogens in the second example. So the negative charge is going to attack the vicinal hydrogen. We're going to push the electrons that were once carbon-hydrogen electrons to be now between the 2 carbon atoms. The 2 are the haloalkane carbon along with the adjacent carbon. Then we're going to push off the bromine because leaving groups just leave. I'm going to redraw the entire carbon framework. I don't lose any carbon atoms. Then I'm going to replace the bromine with a double bond between what was the haloalkane carbon and that carbon that was bonded to the vicinal hydrogen. Just like the previous example, I could have attacked a different position. Okay, there's a separate pair of vicinal hydrogens on the top. As long as there was another vicinal hydrogen I could have grabbed. In this case, it wouldn't have made a difference. There's only one possible product. In this case, it's cyclohexene. Okay, so LDA, we have a negative charge. Now I'm at the dot, so I'm going to go next door. I'm going to go to this carbon atom, and I see that there are 2 hydrogen atoms there, and those 2 hydrogens are our vicinal hydrogens. So we only have 2 in this case. Just like before, it doesn't matter which of the vicinal hydrogens I grab, I'll get the same product in either case. Let's consider it. Negative on the E2 base attacks the vicinal hydrogen. That pushes the carbon-hydrogen bond to make down, or up in this case, I guess, to make a carbon-carbon double bond after we eject the chlorine atom. Always 3 arrows for an E2 reaction. Okay, grab the hydrogen, make the double-double bond, push off the haloalkane leaving group. That's going to give rise to this. Now, you'll notice that sometimes, and I almost did it because sometimes people want to draw all of the bonds, but remember, this actually, remember, we just redraw the carbons and add a double bond between the adjacent carbon and the carbon that was attached to the halogen. You don't want to add extra carbons. And that's something that can happen quite easily if you're not careful. So don't add extra C's. Okay, now this last example I think was an important one to pick. It's actually not an E2 reaction. In this last example, if you recall, the first thing we want to do is figure out how many vicinal hydrogens that we have, because the vicinal hydrogens tell us where the E2 base can go. Well, in this case, there are no vicinal hydrogens. So this E2 base that is desperate, absolutely desperate to do an E2 reaction, can't find one. The O negative instead adds to the CH3 to form an SN2 product. I'll draw that in black. So this one's a little bit of a trick. There's no E2 reaction here, and so this is forced to do SN2. This is forced to do an SN2 reaction. Okay, so it was a little bit of a trick because the first thing you want to do, but I think it's helpful because it points out what we need to do when we're doing an E2 reaction. We need to identify the vicinal hydrogens first, then consider the mechanism, and then draw the products for the reaction. So find the vicinal hydrogen atoms. Maybe look at all of them, count them all. You know, if you've got 6, count all 6, make sure they're the same. In the next video, we'll look at what happens when there are multiple products. But what I want to do to finish up this video, I know it's on the longer side, but let's just wrap up, is why don't E2 bases do SN2 reactions? They're negatively charged things. And so what I'm saying is that with an E2 base, if you've got if you don't have vicinal H atoms, you do an SN2 reaction. But really that's just for when you have CH3 attached to X. Anything else, you actually probably won't see a productive reaction. So SN2 reaction or no reaction. Okay, but what an E2 base actually prefers an E2 reaction in a lot of instances when you have the vicinal hydrogens present. And I don't want to spend too much time looking at the right pathway where it could trick you. I mean, it's helpful to mention it just so that I continue to encourage you to look for vicinal hydrogens and also to recognize that CH3 groups don't have an adjacent carbon atom to provide vicinal hydrogens. But why do we go down the left side? Why don't we do the right side, even when there are vicinal hydrogens present? And the reason why is because E2 bases are too sterically hindered, or too hindered by sterics. That's a better phrasing. Too hindered by sterics to do SN2 reactions on anything other than CH3 attached to bromine or iodine, really. So unless you have methyl bromide or methyl iodide, iodomethane, bromomethane, whatever, CH3 directly attached to the halogen, unless you have those, you're not going to see any SN2 reactions. You're only going to see E2 reactions, or if you really strangle the molecule so it doesn't have vicinal hydrogens, no reactions. But I don't want to look at that too much. I do want to bring up the fact, though, that the E2 bases that we showed have a lot of steric hindrance on them. We've got these big, bulky tert-butyl groups on, or the one tert-butyl group, excuse me, on potassium tert-butoxide, and the two still fairly big isopropyl groups on lithium diisopropyl amide. So for our E2 bases, what I'm saying is these big groups provide enough steric hindrance. Now, what that means is you're not going to see backside attack. The molecule just can't fit in a position such that it can push off the halogen atom on anything more complicated than CH3Br. So no backside attack, no SN2 reaction, no inversion configuration, all of that. Rather, it's going to look for adjacent hydrogens, vicinal hydrogens from adjacent carbons, pull them off, and do E2 reactions. Okay. So this can be a complicated reaction. What I want you to do is break it down. Practice looking for vicinal hydrogens. Just look for vicinal hydrogens, aka adjacent hydrogens. These hydrogens attached to adjacent carbons. Get comfortable looking for those. Once you do that, then you can practice the mechanism 3 arrows. You deprotonate, that is, you grab the hydrogen, you make the carbon-carbon double bond, and you push off the leaving group. Always 3 arrows for an E2 reaction. It is something that's manageable and that we can practice.